The objective of this lecture is to provide a further explanation of the application of Newton's second law to problems in particle kinetics where the particle moves while in contact with either a one-dimensional curve or a two-dimensional surface. The focus of this lecture will be on deriving differential equations when the particle is subject to the two common types of friction forces of viscous friction and Coulomb friction. So we'll title this lecture Application of Newton's second law to particle kinetics problems involving contact. So the important aspect of this is going to be contact. So we have the following setup. When a particle of mass m moves while in contact with either a one-dimensional rigid curve or a two-dimensional rigid surface, the surface, or the curve, or the surface exerts a contact force on the particle. Now this contact force has the general form. And the general form is going to be F sub c, which is the contact force, is equal to N plus F sub F, where N is equal to the normal force exerted by either the curve or the surface on the particle, and F sub F is the friction force. Now, the way this works is as follows, is that we have two different situations. We have a curve and we have a surface. Now remember that in the case of a curve, we're going to get one differential equation. It's 1 degree of freedom which implies one differential equation. In the case of a surface, that's going to be 2 degrees of freedom which implies we're going to get 2 differential equations. Now, in either a curve or a surface, if a particle is moving in contact with a curve or a surface, we have two different types of friction. So, 2 types of friction. The first type of friction is viscous friction, and the second type of friction is Coulomb friction. So the objective is to characterize the forces and determine the differential equations of motion. The way we're going to do that is we're going to need to apply Newton's second law. Now, the form in which we're going to apply this is as follows. It's going to be F is equal to MAPI. So F is the resultant force acting on the particle. P is the particle itself, and it has mass m. And then I is an inertial reference frame. And then m is the mass of the particle. I already said that, so don't need to say it again. And then API is the acceleration of P as viewed by an observer fixed in the inertial frame. So, in the case of particle contact, we actually can decompose the force nicely into the following pieces. We can say let F equal the normal force plus the friction force plus a force I'm going to call F sub E. Now, F sub E is then equal to F minus N minus F sub F, which is actually can be labeled as all forces acting on P. I should say all forces other than N and F sub F acting on the particle. So we're going to use this this notation throughout the discussion. So let's make sure that we label this correctly. It's F sub E. Now we have two different situations. We have a curve and we have a surface, and then we have viscous friction and we have Coulomb friction. So we're going to handle each type of friction for each situation, a curve and a surface, separately. So the first one is going to be particle moving in contact with a curve, or a one-dimensional curve. Okay? So, in order to do this, is I'm going to say let C be a one-dimensional curve. I'm going to say rigid curve. In three-dimensional Euclidean space. And in this particular case, so actually before we do that, we'll say let ET, EN, EB be an intrinsic basis relative to the curve. So in this particular case, the normal force exerted by C on P has the form N is equal to n sub n times En plus n sub b times EB, where En and EB are the principal unit normal and the principal unit binormal to the curve, and ET, of course, is the tangent vector to the curve. Now, given that model for the normal force, we're going to deal with both types of friction. So let's first analyze viscous friction. Now, in the case of viscous friction, the friction force model is equal to minus c times the velocity of p as viewed by an observer fixed to the curve, which is equal to minus c times the speed relative to the curve times the tangent vector, where Vp is the velocity of p as viewed by an observer fixed in C, and Vpc, which is equal to the magnitude of this velocity, is equal to the speed of p as viewed by an observer fixed in C. Now, given this model, we can actually now write the force. So the force is equal to N plus F sub F plus everything else. But because I have a model where the friction force is viscous friction, this gives me N sub N, En, plus N sub B, Eb, minus C times the speed times the tangent vector plus F sub E. So now look what happens. We have three components here. So the three components are going to be the three components along ET, En, and EB, because those are the key directions that allow us to be able to decompose the force. So look what happens if I take F dotted with ET. Well, F dotted with ET is equal to N plus F sub F plus F sub E dotted with ET. And that has to equal the mass times the inertial acceleration dotted with ET. But look what happens when I do that. N dotted with ET is 0 because N is equal to N sub N En plus N sub B Eb, and En and Eb are both normal to ET. And then F sub F, if you go back, you'll see that F sub F is equal to minus C times the speed relative to the curve times the tangent vector. So this gives me minus C times the speed as viewed by an observer fixed to the curve plus F sub E dotted with ET is equal to MAPI dotted with ET. And you can see that in this equation, there are no unknown reaction forces. So because there are no unknown reaction forces, this result is the differential equation. Now remember that in the case of a curve, there is only one differential equation because it's 1 degree of freedom. So as a result, for viscous friction, we get the differential equation without having to know anything about the normal force. So you should write that down. The differential equation in the case of viscous friction for motion of a particle on a curve or on a rigid curve requires no knowledge of the normal force. And the reason is because the friction force model does not contain anything about the normal force. It's purely a function of the speed relative to the curve or the velocity relative to the curve. It doesn't have anything to do with the normal force. But now, let's look at the case where we have Coulomb friction. So now it's Coulomb friction, and again, we're still dealing with the case of a particle moving while in contact with the curve, or with the curve. So the friction force in the case of Coulomb friction is minus mu times the magnitude of the normal times the tangent vector. So now let's go back and do this analysis again. What is F? F is equal to N plus F sub F plus everything else, which is equal to N sub N, En, plus N sub B, Eb. Now in this case it's minus mu times the magnitude of the normal times the tangent vector plus F sub E. So now look what happens when we take the component along the tangent vector. What do we get? Well, I get N plus F sub F plus F sub E dotted with ET. And that has to equal the mass times the inertial acceleration dotted with ET. But in this case, again, N dotted with ET is 0. But in this case, the friction force dotted with ET, it's equal to minus mu times the magnitude of the normal, and then ET dotted with ET is 1, plus F sub E dotted with ET is equal to the mass times the inertial acceleration dotted with ET. So you can see that at this step, we don't have a differential equation because we don't know the magnitude of the normal force. So we need to figure out the magnitude of the normal force. So the magnitude of N still needs to be determined. So we need to obtain this. How are we going to obtain it? Well, we're going to obtain it by looking at the other two components of Newton's second law. So let's look at the En. So let's examine the En and Eb components. Of F equals MAPI. So let's take the En component. What's F dotted with En? Well, if we look at it, it's equal to N plus F sub F plus F sub E dotted with En. And that has to equal the mass times the inertial acceleration dotted with En. So what do I get when I do that? When we do that, N dotted with En, because N has two components, N sub N and N sub B, this gives me N sub N. And then F sub F dotted with En is 0 because F sub F is in the direction of ET, and so I get plus F sub E dotted with En because the second term, F sub F dotted with En, is 0, and that equals the mass times the inertial acceleration dotted with En. Now let's do the same thing for the binormal component. F dotted with EB, actually we can put this on the next page. F dotted with EB is equal to N plus F sub F plus F sub E dotted with EB, which is equal to the mass times the inertial acceleration dotted with EB. So what does this give me? This gives N sub N plus En plus N sub B EB. So if I take the dot product with EB, I get N sub B. And then F sub F dotted with EB again is 0. So I get plus F sub F dotted with EB is equal to the mass times the inertial acceleration dotted with EB. So we have two equations. Notice what these two equations are. I have N sub N plus F sub F, F sub E. F sub E. So F sub E dotted with En is equal to the mass times the inertial acceleration dotted with En, and then I have N sub B plus F sub E dotted with EB is equal to the mass times the inertial acceleration dotted with EB. So from these we can actually solve for n sub n and n sub b. N sub n is equal to what? Well, let's move this a little bit. N sub n is equal to, it's equal to the mass times the inertial acceleration minus F sub e dotted with En, and N sub b is equal to the mass times the inertial acceleration minus F sub e dotted with E sub b. So I've got these two equations. You see that? Now, the magnitude of n is equal to n sub n squared plus n sub b squared to the 1/2. So this result, using these two components, now you'll see that n sub n and n sub b are both known, are both completely known, because I know everything on the right-hand side here, because there are no unknown reaction forces. I've just solved for those two components. So this can be substituted. You can substitute into the ET component. So the differential equation is still obtained the same way. We still get that result for the differential equation, which gives us minus mu times the magnitude of the normal plus F sub e dotted with ET is equal to the mass times the inertial acceleration dotted with ET. This is still the differential equation, but it requires an additional step. So the result here is as follows, is that the differential equation requires knowledge of the magnitude of the normal force. In the case of Coulomb friction, when a particle moves in contact with a curve. Now what's important here is that this magnitude of the normal force is found by solving for the En and Eb components of n, and using the result to obtain the magnitude of n. Then the magnitude of n is substituted into the ET component of F equals ma to obtain the differential equation. So that summarizes what happens in the case of Coulomb friction for a particle moving while in contact with a curve. So we've summarized two things here. One, viscous friction, where there's no knowledge required of the normal force, and the differential equation is just obtained by taking the tangential component, where it's the tangent to the curve. And in the case of Coulomb friction, we need to solve for the two components of the normal force, and then solve for the magnitude of the normal force from those two components, and then substitute the result into the tangential component. So the next thing we need to deal with is a particle moving in contact with a surface. So if you go back over here, we started with this whole result particle moving in contact with a curve, we're now going to go to a particle moving in contact with a surface. Now, let S be a two-dimensional surface. It's a two-dimensional, rigid surface. And also, let T1, T2, and N be a right-handed orthonormal basis for E3 that has the following properties. So here are the properties. T1 and T2 lie in the tangent plane to the surface at the point of the particle. And N lies in the direction normal to the tangent plane to S at P. And because this is a right-handed orthonormal basis, so because it's a right-handed orthonormal basis, we have the property that T1 dotted with T2 is equal to T1 dotted with N, which is equal to T2 dotted with N, which is equal to 0. And we have the property that T1 crossed with T2 is equal to N. So that makes it so that all these vectors are orthogonal and they satisfy the right-hand rule. So now, let's deal with each type of friction that we're going to encounter in problems with particle moving on a surface. So the first one is going to be viscous friction. So in the case of viscous friction, now there's no unique tangent direction because the surface, the tangent, is a plane. It's no longer a tangent vector. It's a tangent plane. So the friction model for viscous friction is equal to minus c times the velocity as viewed by an observer fixed to the surface. So this VPS is equal to the velocity of P as viewed by an observer fixed in S. Now, as a result of that, we can actually start moving through the case of viscous friction. So the force acting on the particle is equal to N plus F sub F and plus F sub E. But in this case, N is equal to N times the unit normal to the surface, right? So this is the model that we use for the force exerted by a surface on a particle. So as a result, we wind up with F is equal to N plus F sub F plus F sub E, which is equal to N times N minus c times the velocity as viewed by an observer fixed to the surface plus n times n minus c times the velocity as viewed by an observer fixed to the surface plus f sub e. So now, the two components that are going to give me the differential equation are going to be the T1 and the T2 components. So if I take f dotted with T1, I get n plus f sub f plus f sub e dotted with T1. What does that have to equal? Well, n dotted with T1 is 0 because n lies in the direction of n. So this gives me minus c times the velocity of p as viewed by an observer fixed in s dotted with T1 plus f sub e dotted with T1. And that has to equal the mass times the inertial acceleration dotted with T1. So from this, we actually get the following result. We get that minus c times the velocity as viewed by an observer fixed in s plus f sub e dotted with T1 is equal to the mass times the inertial acceleration dotted with T1. And you can see that because there are no unknown forces, that gives me the first differential equation. Now in this case there are two differential equations because we're dealing with a surface, as we said at the beginning. So we also have to do the T2 component. So the T2 component gives me f dotted with T2, which is equal to n plus f sub f plus f sub e dotted with T2, which is equal to minus c times the velocity as viewed by an observer fixed to the surface dotted with T2 plus f sub e dotted with T2. And that has to equal the mass times the inertial acceleration dotted with T2, from which we actually get the second differential equation, which is minus c times the velocity as viewed by an observer fixed in s plus f sub e dotted with T2 is equal to the mass times the inertial acceleration dotted with T2. And this is the second differential equation. So we have two differential equations, and again, see what the result is in the case of viscous friction. So in the case of viscous friction, so the differential equation in this case the differential equations are obtained without requiring any knowledge of the normal force. You don't need to know anything about the normal force other than its direction. That's it. We don't need to know anything about solving for the normal force. It's unnecessary. And that's a nice fact. So this is in the case of viscous friction. In the case viscous friction for a particle in motion on a surface, while in contact with a surface. All right, but now let's look what happens when we actually are dealing with the case of Coulomb friction. So Coulomb friction changes the problem again from what it was in the case of viscous friction, just like it happened when we were dealing with a curve. So here's what happens in the case of Coulomb friction. The Coulomb friction model has the following setup. It's minus mu times the magnitude of the normal times the velocity of p as viewed by an observer fixed in s divided by its magnitude. Now, if you look at that, that's a very different model because now it includes the magnitude of the normal. So we can actually use that, and we can recall again that the normal force is equal to n times n. It's the same as it was before. Now the total force is equal to N plus F sub F and then plus F sub E. But in this case, it's equal to N times N minus mu times the magnitude of the normal times the velocity as viewed by an observer fixed in S divided by its magnitude, and then plus F sub E. So now look what happens when we take the two components along T1 and T2. F dotted with T1, which is equal to N plus F sub F plus F sub E dotted with T1 is equal to what? Well, if I take the T1 component, what do I get? The normal force disappears, and I'm left with minus mu times the magnitude of the normal times, I get VPS dotted with T1 all divided by the magnitude of VPS plus F sub E dotted with T1. And that has to equal the mass times the acceleration in the inertial frame dotted with T1. So now let's look at the T2 component. F dotted with T2 is equal to N plus F sub F plus F sub E dotted with T2, which is equal to, well, again, we take the dot product N dotted with T2 is 0, so we get minus mu times the magnitude of the normal times the velocity of P as viewed by an observer fixed in S dotted with T2, all divided by the magnitude of the velocity of P in S, plus F sub E dotted with T2. And that has to equal the mass times the inertial acceleration dotted with T2. And you can see in this case, both of these equations, the T1 and the T2 components, have this unknown normal force in it, the magnitude of the unknown normal force. So in order to be able to determine the differential equations, we need to solve for that unknown magnitude of the normal force. So we need to determine the magnitude of N, and then we can substitute in. So how are we going to get that? The magnitude of N, so we can actually say this, which is determined or obtained by taking the component of F equals ma in the n direction. So what happens when we do that? So if I take F dotted with n, I get n plus F sub F plus F sub E dotted with n. But that is equal to the component n, and then there's no friction force because in this direction, and I get plus F sub E dotted with n, and that has to equal the mass times the inertial acceleration dotted with n. So from this I can actually solve for n. You get n is equal to the mass times the inertial acceleration minus F sub E dotted with n. And now, because this is a scalar, it can either be positive or negative, which means that the magnitude of n is equal to the absolute value of n. And then this can be, make sure this is not a vector, it's the absolute value of n. And this can be substituted into the T1 and T2 components of F equals MAPI. So those, then you get the differential equations. So what happens is that then, using the magnitude of n, which is obtained from the n component of F equals ma, the two differential equations are obtained as, and what do we have here? We have minus mu times the magnitude of the normal times the velocity of p and s dotted with t1, all divided by the magnitude of the velocity of p and s, plus fe dotted with t1 is equal to the mass times the inertial acceleration dotted with t1. This is the first differential equation. And then the second differential equation is minus mu times the magnitude of n times vps dotted with t2, all divided by the magnitude of vp in s, plus f sub e dotted with t2 is equal to the mass times the inertial acceleration dotted with t2. And this is the second differential equation. And so we have the two differential equations where n, or where the absolute value of the magnitude of n is equal to the absolute value of n, which is equal to what I wrote down before, the mass times the inertial acceleration minus fe dotted with n. And so we have all the information we need. We substitute that in and we get the two differential equations. So what's the result here? The result is that the differential equations require knowledge of the magnitude of the normal force. This magnitude of the normal force is obtained from the component of F equals ma in the n direction, where n is the unit normal to the surface at the point of the particle. So in other words, it's where the particle is located instantaneously. And that gives us two differential equations. So again, we see the same result for the case of a particle moving on a surface as we did for a curve, which is that we have two tangential components, or two components that lie in the tangent plane of the surface. And in the case of viscous friction, you get the differential equation straight away by taking the dot product of F equals ma in the T1 and T2 directions, and we don't need any information about the normal force. In the case of Coulomb friction, we need to know the magnitude of the normal force in order to be able to obtain the differential equations. So after taking the dot products in the T1 and T2 directions, we also have to take the dot product in the n direction, solve for the component of the normal force in that direction, normal to the surface, take its absolute value to get its magnitude, and substitute that into the results from the T1 and T2 components in order to get the differential equation. Now, in order to be able to see how this actually plays out, let's study two examples in order to make it clearer how this actually works in practice. So hopefully these examples will help. The first example is as follows. It's a problem that was studied in an earlier lecture, which is a particle moving on a parabola. So I have a particle that's sliding on a parabola. Now the parabola rotates about the vertical with an angular velocity omega. So this problem was explained earlier, but I'll go through some of the basics again now so that we have a description of it for this particular case. Now in this case I have gravity acting downward, and we're going to assume in this case that we have Coulomb friction, because Coulomb friction is the one that actually causes the more issues than viscous friction, because we have to do more work in order to be able to get the differential equation. So I'm going to focus on Coulomb friction in this particular example. Now, without getting into a lot of the kinematics in this problem, we actually solved this problem using a basis that was fixed to this track. And so I'm going to define this basis, Ex, Ey, Ez, and this basis, Ex, Ey, Ez, is fixed in T, and the equation for the parabola, if you recall from earlier, was y is equal to x squared over 2b, and then this parabola, we labeled it as t, which is the track. So the acceleration, just so that we have it, not that we're really going to use it, but the acceleration of the particle as viewed by an observer in the inertial frame, where the inertial frame was the frame relative to which the parabola rotated, this is equal to x double dot minus omega squared x times Ex plus x dot squared plus x double dot all divided by b Ey minus 2 omega x dot Ez. And I remind everyone that we had assumed that the magnitude of omega was equal to omega, and that's equal to a constant. And as a result, and the inertial frame, I, was the inertial frame, and it was the frame relative to which the parabola rotated. So as a result, we got that for the acceleration. Now, we're going to focus on the kinetics, because really the kinematics are not the main focus of this particular lecture, but we did a little bit of the kinematics just as a reminder, but we're going to go to the free body diagram. So when I draw the free body diagram of this particle, I have gravity acting downward. I also have a friction force, and I have a normal force. Now let's identify these things. Gravity acts in the minus Ey direction, and in this case that's what I actually called for all forces other than the friction force and the normal force. That's the only other force acting on the particle. N, because we're dealing with a curve, has the form n sub n En plus n sub b Eb, and as a result, that's the model for the normal force. And then the friction force is equal to minus mu times the magnitude of the normal times the tangent vector. So now let's look and see what happens here. Is that the tangent direction is the direction that is tangent to the curve. It's not tangent in the inertial frame. It's tangent to the curve. So if I actually draw the parabola again, and I look at the location of the particle, this direction is the tangent direction. It's tangent to the curve. This direction is the normal direction, and then Et cross En gives me Eb, which is normal to the plane of the parabola. Now, in order to be able to do this problem, we would actually have to compute all three of these directions in order to be able to do this. But for the purposes of what we're doing here, I'm going to go through and do the force analysis without actually computing them, because things decompose relatively straightforwardly even without having to go through the step of computing these three vectors. So let's actually write this down. So the force is equal to N plus F sub F plus mg. And that has to equal the mass times the inertial acceleration. So look what happens now if I take the ET component. The ET component gives me F dotted with ET is equal to, well, I've got N plus F sub F plus mg dotted with ET. But that is equal to, N dotted with ET is 0. So I get minus mu times the magnitude of the normal, and then I get plus mg EY dotted with ET. Actually, it's minus. This is a negative sign. And then I have that equals the mass times the inertial acceleration, but the inertial acceleration is what I have up there. I don't need to take these dot products. I just can leave it that way. The mass times the inertial acceleration dotted with ET. But you can see that I need to know this magnitude of the normal force. So in order to do that, I'm going to compute the components along the EN and the EB direction. The EN component is N plus F sub F plus mg dotted with En, which is equal to, I get N sub N, and then F sub F dotted with En is 0, and I get minus mg Ey dotted with En, which is equal to the mass times the inertial acceleration dotted with En, from which I can solve for N sub N, and I get N sub N is equal to the mass times the inertial acceleration plus mg Ey dotted with En. And now I can do the same thing for the EB component. I get N plus F sub F plus mg dotted with EB is equal to N sub B minus mg Ey dotted with EB, which is equal to the mass times the inertial acceleration dotted with EB. And that gives me the binormal component as the mass times the inertial acceleration plus mg Ey dotted with EB. And now I can substitute these two into the other equation, and I can get the magnitude of N is equal to N sub N squared plus N sub B squared to the 1/2, and then I can substitute that into the tangential component. So the tangential component is then gives me, I get minus mu times the magnitude of the normal, and then I get minus mg Ey dotted with ET is equal to the mass times the inertial acceleration dotted with ET, where this is substituted. So you substitute into the ET component, and that gives me the differential equation. So this is the differential equation in this particular case. And you can see that once again we needed knowledge of the magnitude of the normal, otherwise we couldn't do this problem. We have to have that, right? So that's the first example. The second example that I'm going to do is going to be this particle that was sliding on a cone, and we did this in some detail again, so I don't want to go through all the details now, but let's sort of revisit some of the details just so that we remind ourselves as to what the setup was. So let's draw the picture somewhat reasonably so that we can get a fair representation of this cone. So there's the cone, and let's make that straight. So now remember that the particle of mass m was located on the cone, on the inside of the cone, and what I had done was I had said that the projection of P into the horizontal plane, which I defined as EX, EY, this position was measured from point O, which was the apex of the cone, and the cone had a half angle. The half angle was beta, and then this vertical direction was EZ. And what we had done was we had gravity acting downward, and again I'm going to put a Coulomb friction force here. So Coulomb friction with a friction coefficient mu. And if you remember, when we solved this problem, we did it in a cylindrical basis, which had its directions along OQ and then EZ crossed with that direction OQ and then E theta and then EZ itself. So E theta was equal to EZ crossed with ER. And if you recall, the acceleration of the particle as viewed by an observer in the inertial frame, which this cone, which I called S, which is equal to the cone, was equal to the inertial frame. And so when we actually go through this, I actually label this the inertial frame. So this is the acceleration of P as viewed by an observer fixed in S, because S was the inertial frame. This was equal to R double dot minus R theta dot squared ER plus 2 R dot theta dot plus R theta double dot E theta, and then I had plus R double dot times the cotangent of beta times EZ. And this angle here was theta, and this distance was r, and that's how we actually got that. Now let's look at the differential equations for this problem in the presence of Coulomb friction. So if we draw the free body diagram, we have to apply Newton's second law. So we have the free body diagram, and the free body diagram looks as follows, which is that we have mg acting downward, we have a friction force, and we have a normal force. Now in this case we're dealing with a surface, and because we're dealing with a surface, the normal force, let's do mg first. Mg is equal to minus mg times Ez. The normal force in this case is equal to n times the unit vector normal to the surface, and the friction force is equal to minus mu times the magnitude of the normal times the velocity as viewed by an observer fixed to the surface divided by its magnitude. And the velocity as viewed by an observer fixed to the surface is actually the inertial velocity in this case, because the cone is the inertial frame. So we actually get a fairly straightforward result for the velocity as viewed by an observer fixed to the surface. But I won't go into the details here because it's not really the main point of what we're doing. But I need to get three directions. Now recall, we need to construct a basis which I called T1, T2, and N, such that T1 and T2 are in the tangent plane to S at P, and N is orthogonal to this tangent plane. Now, we did this problem before, and when I actually did it, we actually had the following results, which were that the unit vector normal to the surface was equal to the gradient of f divided by the magnitude of the gradient of f. F in this case was a function of r, theta, and z, and it was equal to r cotangent beta minus z equals 0. So the gradient of f was equal to the partial of f with respect to r times er plus 1 over r, the partial of f with respect to theta times e theta, and then the partial of f with respect to z times ez. This was equal to the following. I got cotangent of beta times er minus ez. Now, the magnitude of this, if you remember, was equal to the square root of cotangent squared beta plus 1, which was cosecant squared beta, which gives you cosecant of beta, which is 1 over the sine of beta. So as a result, we wound up with n was equal to, we multiply through by sine, cotangent is cosine over sine, so we get cosine of beta times er minus the sine of beta times ez. And then, without going into all the details, recall from earlier, the earlier study of this problem, that T1 was equal to E sub theta. And we actually got that because that was equal to the rate of change of n in S divided by its magnitude. That's because the rate of change of n in S is orthogonal to n. And then we got that T2 was equal to n crossed with T1, which was equal to, well, when we do that, cosine beta er minus the sine of beta times Ez crossed with E sub theta, which gives that T2 is equal to ER crossed with E theta is EZ, and EZ crossed with E theta is minus ER. So I get sine beta ER plus the cosine of beta times EZ. So now I have T1 and T2. So now what we can do is we can take the components. So let's write the force. So if we go back and we look at the force, we have the force is equal to N plus F sub F and then plus mg, which is equal to N times N, and then we've got minus mu times the magnitude of the normal, and this was the model that we had written down over here, times the velocity of P in S divided by its magnitude, and then minus mg Ez, right? So the first thing I was going to do is I'm going to take the dot products in the direction of T1 and T2. So F dotted with T1 is equal to N plus F sub F plus mg dotted with T1, which is equal to, well, N dotted with T1 is 0, so I get minus mu times the magnitude of the normal times VP S dotted with T1, all divided by the magnitude of VP and S, and then I get minus mg Ez dotted with T1. But T1 is equal to E theta, right? So that's what we had described over here. T1 is equal to E theta. And as a result of that, because T1 equals E sub theta, F dotted with T1 is equal to minus mu times the magnitude of the normal times V, P, and S dotted with T1, all divided by its magnitude. And that has to equal the mass times the inertial acceleration dotted with T1. But in this case, since T1 is equal to E theta, look at what that comes out to be, because the acceleration has 3 components. So this just becomes the mass times 2 r dot theta dot plus r theta double dot, right? But the problem is we still have an unknown component of reaction force there. So let's go on to the T2 component and the N component, and we'll resolve that reaction force. F dotted with T2 is equal to N plus F sub F plus mg dotted with T2, which is equal to, well, N dotted with T2 is 0, so I get minus mu times the magnitude of the normal times VPS dotted with T2, all divided by the magnitude of VP in S. And then I've got minus mg EZ dotted with T2. But T2 is equal to, it's actually over here, sine beta ER plus cosine beta EZ. So the only term that is going to affect anything here in the gravity component is going to be the cosine of beta. So this gives me minus mu times the magnitude of the normal, and then times, I've got VPS dotted with T2, all divided by the magnitude of VPS. And then I get minus mg times the cosine of beta. And that has to equal the mass times the acceleration in the, I should actually say the frame S, which is the inertial frame in this case, dotted with T2. And that, if you look at this, because T2 is equal to sine beta ER plus cosine beta EZ, if I'm going to take the acceleration, I'm going to only be taking the ER and the EZ components. So the ER and the EZ components are R double dot minus R theta dot squared plus R double dot cotangent of beta. So what I get here is I get this is equal to the mass times R double dot minus R theta dot squared times the sine of beta, and then I get R double dot cotangent of beta times the cosine of beta. And that gives me the result for the T2 component. Now notice that the magnitude of n appears in both the T1 and T2 components of F equals M A P S. So we need to solve, I can actually put it here. So we need to determine, or we need to obtain n, the magnitude of n. So how are we going to do that? So we obtain the magnitude of n from the n component of F equals MAPI. How do we do that? Well, F dotted with n is equal to n plus F sub F plus mg dotted with n. But that's just equal to capital N, and F sub F dotted with n is 0. And I get minus mg, this is EZ, dotted with n. And n, if you remember, was equal to cosine beta ER minus sine beta EZ. So this gives me n plus mg times the sine of beta. And as a result, that has to equal the mass times the inertial acceleration dotted with n, which gives me that n is equal to the mass times the inertial acceleration dotted with n minus mg times the sine of beta. And you remember that this is because n is equal to cosine beta ER minus sine beta EZ. So as a result of that, we can now solve for the magnitude of n. The magnitude of n is then equal to the absolute value of n, which is equal to the absolute value of the mass times the inertial acceleration dotted with n minus mg times the sine of beta. And then we substitute this into, the T1 and T2 components to obtain the two differential equations. And I'll remind everyone that the T1 and T2 components are these two components. This one right here, which I could label now with a star, that's the first one, and this one here, which is the second one. And so as a result, these two components, we substitute in the value of n, because you notice that the value of n appears in both these components. We have the magnitude of n, which is equal to the absolute value of n, and we substitute them in to get the two differential equations. So the upshot of this lecture is that we have characterized motion on a curve and on a surface, and we've examined both viscous friction and Coulomb friction, and we developed the results for both types of friction. And then once we did that for a curve and a surface, we applied the results to two examples in particle kinetics, one with a particle sliding on a curve and one with a particle sliding on a surface. So that takes us to the end of this particular lecture. In future lectures, we are going to study particle kinetics in the presence of contact in different examples, and we'll use the results from this lecture along with the results from for the specific problems to be able to determine differential equations of motion with both viscous friction and Coulomb friction. And so that'll be the end of it for this particular lecture, and we'll move on to other examples in the future.